Today the topic of our lecture is failure criteria against the dynamic loading. Whenever you want to design any machine element against a dynamic load, you will have to follow these failure criteria. The first one is Soderberg failure criteria, the second one is Goodman criteria, third one is Gerber criteria, and the fourth one is modified Goodman criteria. We will discuss these criteria, but before this let's discuss some terminologies that will be used in these criteria. But before those terminologies, let's discuss what is dynamic loading. When the magnitude of the load is going to change, then that type of load is called dynamic load. There are different types of dynamic loading, so let's see what is dynamic load from those types. So these are different types. The first one is fluctuating load, and the cycle of the stress for that is called fluctuating stress cycle. You can see at 0 the stress because of the load is at this point. Now at pi by 2 the load have been changed, and because of that the stress at that point has increased. So this is that stress. You can see it is greater than the stress. Now after that the stress again has decreased because of the decreased in the load at that point pi, and for 3 pi by 2 the stress now is equal to this, and at 2 pi or 360 degree the load is this. You can see the cycle that the value of the stress or the value of the load is not constant, it is constantly changing. So you can say that this is the dynamic load. Here this value is the maximum value, so I will represent the stress at this point by sigma max, means the maximum stress, and this is minimum stress. Now the definition for the fluctuating load is that when sigma max is not equal to sigma minimum and both have positive signs, then that type of load is called fluctuating load. And in case of alternating, this one is sigma max and this one is sigma minimum. You can see that sigma max is not equal to sigma minimum, and sigma max have positive sign and sigma minimum have negative sign. So this is the definition, means for alternating load the sigma max will not be equal to sigma minimum, and sigma max will have positive sign, sigma minimum will have negative sign. And for the completely reverse load, in the definition, a completely reverse load will be that load where this sigma max will be equal to this sigma minimum, and sigma max will have positive sign and sigma minimum will have negative sign. And for the repeated load, the sigma minimum will have 0 value and sigma max will have some value in the positive direction. So this is the definition for different types of the dynamic loading, and from the diagram you can see that the value of the load or the value of the stress is constantly changing, so that is why it is called dynamic loading. Now here sigma max minus sigma minimum divided by 2 is called sigma variable, or the variability in stress. So for this fluctuating, repeated and alternating, the value is less than the sigma max for the sigma variable. And for this completely reversed load, sigma variable is equal to sigma max, and for the static load sigma variable is equal to 0. I have discussed it in my previous lecture, so if you want to know about this you can go to that lecture and see over there how it is equal to 0. After that let's talk about sigma mean or average stress, that is equal to sigma max plus sigma minimum divided by 2, and it is equal to sigma max for the static load and it is less than sigma max for these three. But in case of this completely reversed, it is equal to 0. So sigma variable is equal to sigma max for completely reversed load, but it is equal to 0 for static load, and sigma mean is equal to sigma max for the static load and it is equal to 0 for the completely reversed load. And for the other three, the sigma variable is in between these and sigma mean is in between these. So the point I want to make over here is that sigma max is equal to sigma variable for completely reversed load, and sigma mean is equal to sigma max for the static load. So later on we will use these in our dynamic loading failure criteria, so keep this in mind. And this is a table where you can see the value of sigma variable or sigma mean for different types of the load. Then after that let's discuss some other terminologies. They are ultimate point, yield point, endurance limit or endurance point, variable stress and mean stress. Variable stress and mean stress have been discussed. Now let's discuss the other three for that. Stress strain curve. This curve is for the ductile material. and this is for the brittle. Now you know that when you increase the load, it will increase the stress in the body, and it will linearly increase the strain in that body. And after this point, if you further increase this stress, it will not linearly increase the strain, so this relationship will not hold after that point, and that point is called proportionality limit, but the body will still regain its shape. And after this point, if you pass through that point, the body will not regain its shape. It is called elastic limit or elastic point. If you increase the stress till this point, then the body will not regain its shape. It will go back to this point. So this point, you can see it is to the right of this 0, means the body has not regained its shape, but this difference is very smaller. Now there is a point called yield point. If you further increase this stress by small amount, it will increase the strain by large amount. So that point is called yield point, and here in this diagram, this is that point. It is considered to be failure criteria for the ductile material, because for the small increment of the stress, there is large amount of increment in the strain, and since this strain cannot be reversed, so the shape has been changed, and when the shape is changed, it will not perform its intended purpose. If you further increase the load, it will increase the stress and resist that load, and a point will reach where there will be maximum stress produced in the body, or there will be maximum resistance to the load. But after that, the ability of that body to show the resistance will decrease down like this. So this is the maximum strength of the body, or maximum resistance of the body. So this point is named as ultimate point, and the strength at this point is called ultimate strength. So ultimate point has been discussed, and yield point has been discussed. For the ductile and for the brittle, there is no yield point. There is direct ultimate point. The body will directly fail. In case of ductile, there will be apparent signs for you that the body is going to break, but in case of the brittle, there is no early signs. The body directly fell. So it has been shown that the yield point for the brittle material is this one, but this is not the case. There is no apparent yield point for the brittle materials. Now let's discuss the endurance limit. The endurance limit is the fatigue strength of a body when you want infinite life for that body. This SF is then represented by SE or SE dash. So let's discuss that. For that, take the fatigue strength on y-axis and fatigue life on, or number of cycles on x-axis. Now you know that the strength for the static load, or 10 raised to the power 0 cycle, is equal to SUT, and if you increase the load cycles or fatigue life to 10 raised to the power 1, it will decrease the strength of the body. So now this is the fatigue strength SF for the body. If you further increase the fatigue life, it will further decrease the strength like this. Now there is a point after which there will be no further decrement in the strength by increasing the fatigue life. So this is that point, and after that, the cycles can be named as infinite life or infinite cycle. So there is no further decrement in the fatigue strength, so this is called endurance limit. Now here I want to tell you that SE dash is for an ideal machine element, means that it will have good surface finish. Similarly, there is no notch. There will be a specific temperature at which this will be calculated, and there can be some other things as well. Now if the surface finish is not good, there is a notch, due to it there will be stress concentration, and there is a different temperature under which the element will be loaded. So for that, the endurance limit will be changed, and it will be represented by SE. And when you want to include all these things, it will be equal to Ka, Kb, Kc, Kd, Ke, Kf, and to Se dash. The values of these will be either 1 or less than 1. So Se is less than Se dash. I have discussed this as well in my previous lecture. You can go to that lecture to see it over there. But let's go to the failure criteria. For that, take x and y axis. On the y-axis, I have taken sigma variable, and on the x-axis, I have taken sigma mean. It is because in case of the static, sigma mean is equal to sigma max, and for the static load. And in case of completely reversed, sigma variable is equal to sigma max for the completely reversed load. For all other loads, the value of the mean will be less than sigma max. That is why we have taken this one, and similarly For all other load, the sigma variable values will be less than sigma max. Since these two, sigma mean in case of static load and sigma variable in case of completely reverse load is equal to sigma max, so that is why we have taken them for the graph. And that sigma max in this case should be equal to either yield point or the ultimate point, and in case of variable load it should be equal to the endurance limit or less than that. So for the ductile, let's take this point on this axis and this point on this axis. If we join these 2 points, this line is called Soderberg line and the criteria is called Soderberg-Feller criteria. And here, since this is a line and we know that line equation is given by x by a plus y by b equals to 1, and a is a point on the x-axis where the line will pass and b is the point on the y-axis where the line will pass through the y-axis. In this case, this will be equal to a and this SE will be equal to b, and instead of x we have taken sigma mean and instead of y we have taken sigma variable. So put all these values, it will give you this equation. If you are inside this line anywhere in this region, you will be safe. If you are at this point and this is another point, so this point is more safe as compared to this point. Now if you want to be safe according to this criteria, then divide this by a factor of safety which will be greater than 1. So when you divide sigma factor of safety, it will give you some point over here, so this will be that point. And when you divide this as well on factor of safety, this will be a point somewhere, and when you join these 2 points it will give you this line. Now you will be in this zone. This zone will be safe for you according to this line. But here, since there is no yield point for the brittle material, there is ultimate point for the brittle material. So when you take brittle point and join it with the endurance limit, it will give you this line. This line is called Goodman line and the criteria is called Goodman-Feller criteria. Now instead of sigma y, put sigma ut over here or over here. So this is called Goodman criteria and you will get this equation for the Goodman criteria. Now after the Goodman, there was another scientist who was named as Gerber. He said that above the Goodman line there is some other region as well where the body is safe, and his statement was based on the experiments he did. So he gave this line and it is called Gerber parabola, and for the parabola there will be square in the equation. Just like Goodman, these 2 points are same for the Gerber parabola as well. So if you square this term, it will give you the equation for the Gerber parabola. Now according to this, if you want to be more safe, then divide SE and SU with the factor of safety, and when you do so, it will give you this point and this point, and joining these 2 points with the parabola, it will give you this parabola. Now you will be in the safe zone. So divide this by factor of safety and this is well on the factor of safety. Now when you take it out, it will come over here. This will be square and this will be factor of safety. Now divide factor of safety on both sides, so it will be cancelled from over here and also from over here, so it will become like this. Now there was a scientist called Langer. He joined the yield point of the mean stress axis with the yield point of the variable stress axis. He named this line as yield line or Langer's line, since the line was proposed by the Langer. And for this Langer's line, A and B both will be equal to sigma yield. X will be sigma mean and Y will be sigma variable. So for Langer line, the equation is this, that is sigma mean plus sigma variable is equal to yield point. And you can divide this by factor of safety as well if you want to be safe. Now after that, Goodman came again and said that since this region is not safe because for dynamic loading the body cannot pass through the SE, and similarly he also further said that this region is not safe according to me. So he said that I will take up to this point, he take his own line, and below that he'll take this line and said that this is the modified Goodman criteria. So for that, these equations can be used. These equations for this line and these two equations for this line. This is called modified Goodman criteria. Now, according to modified Goodman criteria, the body will not be saved right after that. But according to the Gerber criteria, the body was safe in this region as well. Soderberg criteria is the most conservative criteria. If you design anything against it, your design will be safe against the other as well. But this criteria is not used most frequently.